Today our topic is coastal protection. Let's now look at the category of cylindrical structures, which applies to vertical piles, horizontal pipelines, as well as cables. The hydrodynamic forces acting on cylindrical structures can be attributed to steady flow as well as unsteady flow. Now, when a steady flow moves past a body, there is a drag force which acts on the body due to frictional shear effect as well as normal pressure. We should have encountered this category of problem before in physics, whereby if we drop an object down a vertical column of water, then the object will accelerate at the beginning due to gravity, and eventually it will be moving at a steady velocity. And different objects with different shape, different roughness will experience different drag force due to the fluid, depending on the types of fluid, the density and the viscosity. Now, for cylindrical structures, although it may not be moving, but when the steady flow velocity moves past the structure, it has exactly the same effect, and which is why cylindrical structures also experience exactly the same type of drag force under steady flow condition. Meanwhile, the coastal environment is dominated by unsteady flow, especially because of the orbital motion of the wave, which produces alternating acceleration and deceleration. This can induce additional forces on the cylindrical structures. When the flow accelerates or decelerates, the pressure on the surface of the object will change. For example, in this case, we're looking at the plan view of cylindrical structures, and these arrows here shows the streamline of flow around the structures. The pressure at this point P1 and the pressure at this point P2 are not the same, and in fact it will changes due to acceleration and deceleration of the flow. Due to the difference of pressure between these 2 points, there is an differential pressure. There's a pressure gradient, and as a result of that, there is a net force that acts on the structure. Another effect is due to added mass. Added mass refers to the force required for the fluid to be displaced in order for it to get around the structures. Now, this added mass effect also contribute to another force towards the body, and it is also known as the initial force. So basically, the hydrodynamic forces acting on a cylindrical structures is made up of two main components. Typically, we are going to refer to the component due to steady flow as the drag force, and the component due to the unsteady flow as the inertial force. With that, we get the Morrison equation, which gives the hydrodynamic forces F acting on cylindrical structures, which is made up of two terms. The first term is a drag force due to velocity u, and the second term is the inertial force due to acceleration du over dt. Here we have the drag coefficient Cd, and 1 plus k is the inertial coefficient Cm, where k is the added mass coefficient. For potential flow, these are the k values for different shapes. For real fluid, the k value will be slightly smaller. Rho here is the density of the fluid. A here is the area in the direction of the flow. So if D is the diameter of the circular cross-section, then area is given by D times L. V here is the volume occupied by the cylindrical structure, so it's given by pi d squared over 4, which is the cross-sectional area of the cylinder, multiplied by L, where L is the submerged length. If we take the expression of the hydrodynamic forces now and divided it by the submerged length, then what we get is the force per elemental length, given by this expression. Now we want to take note here that the drag force is proportional to the diameter d, whereas the inertial force is proportional to d squared. So which means that the larger the size d, then the larger the inertial force will be. We also want to take note that the drag and the inertial force are lagged by 90 degrees. Recall previously that we have when we have a wave and the velocity u is given by this expression and the acceleration is given by this expression. They are out of phase by 90 degrees because the u has a phase term described by cosine function, but acceleration has a phase term described by sine function. So as the wave go through a complete cycle, whenever velocity is at the maximum positive or negative, then the acceleration will be 0, whereas when velocity is 0, then acceleration will be at its maximum positive or negative. So as a result of that, the drag force and the inertial force are also out of phase by 90 degrees. Whenever drag force is maximum or minimum, inertial force will be 0, whereas whenever inertial force is maximum or minimum, then the drag force will become 0. We can look at the effect of the phase difference between the drag force and the inertial force in this diagram. Here we show the complete cycle of a wave profile given as eta, which is the surface water displacement from the still water level. The horizontal axis here is the phase angle, which is kx minus sigma t. K is the wave number and sigma is the wave frequency number. Now assuming that this is a wave passing by and we take a snapshot at this particular instance, so we fix the time. So in this snapshot captured, we are now looking at different position x, and at this different position in this one complete wave cycle, we can see how the drag force changes. Notice that when the wave is at its crest, drag force is at a maximum positive, which drops and becomes 0 when the wave is at the still water level. The drag force continues to drop to become a maximum negative when the wave is at the trough, and after that the drag force rises to become 0 again when the wave is at the still water level, and the drag force rises to maximum positive when the wave is back to the crest. On the other hand, when the wave is at the crest, inertial force is 0. Inertial force rises to a maximum positive when the wave is at the still water level. Inertial force drops to 0 when the wave is at the trough. Inertial force drops to a maximum negative value when the wave is at the still water level, and subsequently the inertial force is 0 again when the wave is at the crest. If we sum up the drag force and the inertial force at each of these locations, kx, then we find that the total force actually follows this pattern highlighted, whereby it is slightly higher than the drag and the inertial force. Somewhere here, and then it falls to minimum right here and goes back up here. So we have a peak positive value right here and the peak negative value right here, which are the same. But the peak force, the peak total force here is definitely not the drag force plus the inertial force without considering the phase angle. If we want to know what exactly is this position, here on the horizontal axis kx, then we can try to work it out from this expression. But usually that is not very important when or at which position that this happens. Usually what we are more interested in is what is the maximum value here, which is the maximum value, the maximum total force subjected by the wave to the cylindrical structures, and this will be the important value that needs to be taken into consideration for the structural design. Both the drag and inertial force are generally function of the structural shape, orientation to the flow direction, prior history of the flow, surface roughness, and Reynolds number. Here in this plot, we see how the drag coefficient depends on the Reynolds number as well as the shape of the object. The plot is obtained from experiments whereby different object shape is being dropped through a vertical column of water. Of course, in the present context, what we are interested in is the drag force on a cylinder, whereby we can see that the drag force is the highest at low Reynolds number, and it drops almost linearly and eventually approaches relatively constant value at higher Reynolds number. That means at higher turbulent flow, we have more or less constant drag coefficient, which is the case for coastal condition. Not only the drag coefficient depends on the Reynolds number, it also depends on the relative roughness on the surface of the object. So we can see here how at different relative roughness, the drag coefficient may vary. Basically, both the drag coefficient and the inertial coefficient changes with time and also changes with position in the water column. In order to select the suitable value to be used in the Morrison equation, typically we choose a constant value that is representative of the peak load, that means peak force, as well as the peak moment conditions. To do that, we can use this simple rule of thumb, how to choose the drag coefficient and the inertial coefficient depending on the Reynolds number, whereby the Reynolds number is calculated based on the wave particle velocity. We want to take note that the Morrison equation is only valid if the structure size is relatively small compared to the wave particle orbit, so that the flow field around the object can be fully developed. In this case, mathematically it can be represented by the condition DOL less than 0.05, whereby D is the cylindrical size and L is the airy wavelength. So essentially, if the size of the cylindrical structures is less than 5% of the wavelength, then the Morrison equation will be valid.